Figure it out. Why is that limit 0? Brittany, you know something?
Well, if f of x can equal f of c,
Yeah. Can you put that together with a little bit more self-confidence? Brittany, tell me one thing about this limit that you know. Is there anything you guys know about this limit? Brittany, what do we know?
f of x can equal f of c because it's if f has a relative max at x equals c, then f of x must be less than or equal to f of c. And in order to get the limit to equal 0, the numerator must equal 0, and so f of x must equal f of c, and that is possible.
Right. Well, we hope that that works out, right? I can't just go using that back. Yeah. Somehow you're right that I somehow need to show that the numerator is 0. But okay. So wait. But what can I say for sure with the information given? You almost had it. I mean, you basically said it, but it was kind of buried underneath some other comments, so it got lost in the shuffle. Kevin, what do I know for sure about that limit? Look at that limit. Let's just start with the limit, right? We just begin. We take the limit. I mean, proof sort of like begins here. We're going to take the limit as x goes to 0 of f of x minus f of c over x minus c. Prove to me that this limit is 0. I demand it. Now, prove to me that this limit is 0.
As x approaches c, or x approaches 0?
C?
Yeah, C.
Thank you. Tell me one thing about this limit that you know for sure.
F of x is
0 or 0.
And thus, Griffin?
at some point the top is 0.
No, f of x is always less than or equal to f of c.
So it's always the top is either negative or 0.
Yeah, that seems relevant, right?
Yeah.
Griffin and Jimmy are telling us something. Say that again.
The top is either negative or 0.
Yeah, the top of the numerator of this fraction is guaranteed to be negative or 0. Do you agree? Because that's just this fact being used right now. Okay, so if the top is guaranteed to be negative or 0, how about what can I say about the bottom? Is the bottom positive or negative?
Depends on where you're
Yeah, it depends on where you are.
Depends on where you're approaching from. So what might be a good idea now?
to approach the left and the right.
Approach to the left and approach to the right. Okay, yeah, so let's do it. Let's take the limit as x approaches c from the left of f of x minus f of c. And we'll take the limit as x approaches c from the right of f of x minus f of c. So we're going to do just like some casework, right? All right, well, if I'm taking the limit as x approaches c from the left, this is the limit as x approaches c from the left. Now we're going to use this observation that you guys just made, right? What can I say about the numerator again? Guaranteed to be?
0 or negative.
Yes, this numerator is guaranteed to be some number which is less than or equal to 0.
Good recovery.
And what can I say about the denominator?
Less than or equal. I mean, less than or equal to negative.
Blah, 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 blah. Denominator, rest of the class. Guaranteed to be negative, because now I'm approaching c from the left. So x's number which is less than c, so this is guaranteed to be negative.
Left. So it's going to be x minus c.
Okay, so if my numerator is less than or equal to 0, and my denominator is less than 0, what can I say about that fraction overall? Or 0. Yes. If you take something which is less than or equal to 0 divided by something which is less than 0, the answer is the limit of something which is greater than or equal to 0. So I claim that this limit is greater than or equal to 0. You with me?
Yes.
Okay, on the other hand, I feel like you guys see the cool thing coming now? Maybe not. On the other hand, what's the limit as x approaches c from the right? Well, what can I say about the numerator now?
Still less than or equal to 0.
The numerator is still guaranteed to be less than or equal to 0 because f of c is a relative max.
But the bottom's gonna be positive.
Since we're approaching c from the right, this denominator is guaranteed to be positive. So what happens when you divide a less than or equal to 0 number divided by a positive number? Yeah, so we're taking the limit of something which is less than or equal to 0, and so that limit must be less than or equal to 0. The limit from the left is greater than or equal to 0, but the limit from the right is less than or equal to 0. So what?
So it has to be 0.
Because it exists. Yes. Because the limit exists, here's when I use my second assumption that the limit exists. Since the limit exists, the limit from the left must equal the limit from the right, and so thus those two numbers have to be equal. Well, what's the only number which is both less than or equal to 0 and greater than or equal to 0?
0.
0. Ta-da! Fermat's theorem proved. How do we feel about this? Alright. So this is pretty great. And what is going on here is, again, Fermat's theorem says, if I have a relative max and the derivative exists, then the derivative must be 0. I'm going to slightly rephrase. So this is a slight logical rephrasing of this statement. If f of c is a relative max, then there are really only two possibilities. Either the derivative exists there or it doesn't, right? So I'll just write either f prime of c does not exist, or f prime of c does exist. But if f prime of c does exist, then Fermat's theorem says that it's 0. So another way of stating Fermat's theorem is to say that if I have a relative max, then at that relative max, either the derivative does not exist or the derivative is 0. Everybody with me? All right. So this is great because this tells me that if I'm searching for relative extrema, where should I search? Yeah, suppose I am looking for relative extrema, just like several of you just said. If I'm looking for relative extrema, where should I be looking? I should look where f prime of x does not exist, and I should also look where f prime of x is 0. Those are the two places where I need to look, because I just proved that if there's a relative max, then one of those things must be true. And so if I look at all these places, then I'll find all the relative extrema that I need to find. Okay, we actually have a name for these things. We call them critical points. And critical points are simply, or some people call them critical values. I call them critical points, but I think our textbook calls them critical values. Critical values are simply x coordinates where the derivative is either 0 or does not exist. All right, let's do a practice problem right now. Should we do an easy one or a hard one? Why do I have all these weird examples? Okay, whatever. So, here is the problem. Take the following function. So, yeah, I'm going to move in a second. Take the following function. F of x equals x root 4 minus x squared on the interval -1, 2. Please find all extrema. In other words, find the absolute max and the absolute min of that function on that interval. Just go here. Sorry. Go. By the way, what's our overall strategy for finding extrema? Oh, I didn't hear anybody. It's like maybe the very, very first thing you should do. Maybe even before that. What are the two things? What are the two places where extrema might be located?
When x is 2 and x is 0.
Zero. Where'd you get zero from?
Oh my god.
Yeah, so try the endpoints. Basically, this really boils down to two tasks. One is check endpoints, and two is relative extrema. So it's really like two separate steps, right? As we've seen from our pictures, which I now erased, the absolute extrema of a continuous function in a closed interval must occur at either the endpoints or the relative extrema. So maybe just like right from the beginning, before you forget, just like compute f of -1 and compute f of 2. What is f of -1? -√3. And what is f of 2? 0. Okay, and now find the relative extrema. How do we find the relative extrema? Take the derivative and look for critical points, right? Because Fermat's theorem tells me that if there's a relative extrema, the derivative must be 0 or the derivative must not exist. So thus, the critical points are the points I should be looking for. So alright, take the derivative, and actually this is a good opportunity for us to practice something which I don't think we've done yet. Or maybe we have. We did in some classes, but not in others. So if we take the derivative, we have to use the product and chain rule, right? So it's like derivative of the first times the second plus the first times the derivative of the second. And the derivative of this is going to be 1/2 4 minus x squared to the -1/2 back inside -2x. Yeah? Okay, so this is 4 minus x squared to the 1/2 minus x squared 4 minus x squared to the -1/2. Alright, so at this point you have some options, and there are some good options and there are some bad options. A bad option is to just descend into a nightmare of like radicals and common denominators and other just like gobbledygook. The smart way to do it, which I'm going to just tell you right now, is to make maximum use of exponent rules. Did we talk about this kind of thing yet? I don't think we did. I think I only did this in one class and it wasn't you guys. So suppose I'm factoring a squared plus a to the 7th. How do you factor that? I should factor out what? A squared. Because if I do that, I get 1 plus a to the 5th, and now I'm happy. Did I have to factor out a squared? Could I have alternatively factored out a to the 7th? Weird, but sure. Yeah, then I would have a to the -5th plus 1, and now I'm not really happy because I have negative exponents, and I don't like negative exponents. Okay, moral of the story, if I want positive exponents, I should always factor out the lower of the two numbers. Okay, well the smooth way to make this problem look really nice all at once is to factor out whatever they have in common. What they have in common is 4 minus x squared. So I'm going to factor out 4 minus x squared. How many 4 minus x squared should I take out? -1/2. That's what we just learned a second ago. What we just learned a second ago is always factor out the lower of the two numbers. If you always factor out the lower of the two numbers, then you'll be left with positive exponents. So if this feels unnatural at first, but then you will like appreciate it as just like the best way to do this algebraically. Because if you factor out 4 minus x squared to the negative 1/2, what are you left with?
4 minus x squared.
You're left with some number of 4 minus x squared. How many? 1. Because by exponent rules, something to the negative 1/2 times something to the 1 is something to the 1/2. And then, what else? Minus x squared. Bam. So the beauty of this approach is to just like instantly like turns your stuff into prettiness just like right away. So this derivative, I will continue to simplify this derivative. This derivative is 4 minus 2x squared over root 4 minus x squared. Or perhaps I could even write it as negative 2x squared minus 2. It wasn't that bad, yeah, but just trust me, there are times.
Oh, yeah.
Okay. Alright, so here we go. Here's my derivative. What was the point of doing that? What are the critical points? What are the critical values? Yeah, critical values are wherever the derivative is 0, which will happen at root 2 and negative root 2, and wherever the derivative is undefined, which happens at 2 and negative 2. Okay, but some of these are irrelevant because they're not on our interval.
Minus 2.
Negative root 2.
So kill, because those are just not on my interval. And I already tested 2, so really all I have to do now is test. By the way, do I know for sure at this moment that this actually is a relative max or a relative min?
Yes.
Yes? Like for sure? No, I think it is actually. But do I know for sure that it is? No. Okay, we have to be. Yeah, we have to be. No. Okay. We have to be a little bit careful here, right? Because notice that this whole critical points thing, all the critical points are the points which might be relative extrema. I don't necessarily know that they are relative extrema, I just know that they might be. If there are relative extrema, then they must be one of these.
Oh, it's not if and only if.
It's not an if and only if, right? That's kind of careful, right? Fermat's theorem says if you have a relative max, the derivative exists and the derivative is 0. So if there's a relative max, the derivative is 0 or it does not exist. But just because the derivative is 0 doesn't mean that there's a relative max, right? We've seen that already. So it's not, I can't say for sure that this is a relative max or min, even though I think it is in this case. But alright, so let's do it. What should we do? We should just plug in root 2 and see what we get. What do we get?
Root 2.
Yeah, you get like root 2 times 4 minus 2, but the square root of that.
So root 2.
So root 2, so it's just 2. Yeah. Okay, so this is kind of awesome. What we have found is that I've checked the endpoints and I have received these two y values back. I've checked the only number which might be a relative max or min, and I received that. And so now I'm prepared to just give the answer to this problem. What is the max of f on the interval -1, 2? Max is 2.
Oh, yeah.
And what is the min of f on the interval -1, 2? The smallest y value. Alright, what does this function actually look like? I just kind of know by experience. Let's see. The domain is going to be everything from -2 to 2, and the sign chart is going to be negative, positive. And here's what I just learned. What I just learned is that it goes to the origin. At 2, it's 0. At -2, it's also 0. And at root 2, it's going to be 2. And it's also true that the derivative is 0 there, right?
Yeah.
So if the derivative is 0 here, I think I kind of, and also this function's odd. So I think I know what this function looks like. It looks like this. And thus is all that kind of makes sense. All right, should we do one more?
Actually,
The other side.
Yeah, I should go outside.
Okay, one more. How did I finish? Yesterday I was like feeling like really like sick.
Good of a teacher for us.
Yeah.
Somehow you guys were like 40 minutes more efficient than yesterday's class. I think there's just a lot of like, a couple certain people in that class who were just like really.
We got this down. Yeah, like yellow.
One more problem. One more problem. F of x equals x minus 2 sine x on the interval 0 to 2 pi. Find the absolute max and min. Go. Actually, you want to do a different problem?
No, this is fine. Yeah, this is fine. Let's do this.
Let's do half the class does one problem and half the class does another. That's kind of fun. Do you guys really think that we're going to go with that?
We'll do mine.
It could, but like.
Yeah, we should go do it.
I feel like I'm responsible. Anyway, but do a problem. Do this problem, and then the other half of the class do this problem.
Which half of the class?
I don't know.
Okay. I'm doing the first.
If your name starts, if your last name starts with A through M, do the first problem. If your last name starts with N through Z, do this one. Go.
It's like me and Richard.
Yoni, what's your last name? What?
I'm doing the second one too.
By the way, for this first one, I kind of already knew that the function looked like that, because like pre-calc techniques alone, you remember this? We did a problem like this once, where this is, except I messed up, so it's actually wrong. Because, right, it's x minus 2 sine x, so it's kind of like the sum of two functions. It's like the sum of
The x function.
the x function and negative 2 sine x function, which means I kind of like draw x and then like at pi over 2, it's going to be 2 less than it would be. So I think it might even be like down here or something, right? So I know it's going to look something like that, but now calculus will tell me exactly where those relative maximum and minima are, which is something I could never do before. I haven't actually done this yet. If I plug in, it's like pi over 3 minus root 3. Are you guys getting what I'm getting?
Yeah.
It's kind of like a gross, it's a slightly gross number. That's like 1 minus, that's like approximately like negative 0.7.
Yeah, it's only plus.
And then this is 5 pi over 3 also minus, no, what am
No, it's
I?
plus.
Negative, now it's like plus root 3, right?
Yeah.
I thought you fixed it.
So that is like 5, I don't know, it's like 6 or something. Not really sure. No, it's like 6.7. So over here at pi over 3, one place the derivative is 0, and then 5 pi over 3 is like another one. Alright, so what is, it's going to be bigger than 2 pi for sure. That's what I know for sure, right? Yeah, so what is the max?
5 pi over 3 plus 3.
Yeah, the max of f on the interval 0 to 2 pi is 5 pi over 3 plus root 3, and the min of f on the interval 0 to 2 pi is just that one, pi over 3 minus root 3. Someone following this?
Yeah.
How about this one? May actually be convenient to pull out the negative. Negative x to the 3/5 x minus 4. And why did I pick the number 6?
Yeah.
Terrible number.
It's a disgusting one. Yeah.
Well, anyway, let's take the derivative. If we take the derivative, this is a good example to use that stuff we learned over there. If you take the derivative, it's the derivative of the first, so it's negative 3/5 x to the negative 2/5 to the first times the second, plus the first, which is negative x to the 3/5 times the derivative of the second, which is 1. So I get this. What's the fast way to factor this out? Take out an x to the negative 2/5. And also take out a negative, she says. If I do that, I will get 3/5 x minus 4 minus, no, and then times an x also, right?
Yeah.
3/5 x. Because it's the 3/5 here, I also have an x, because x to the negative 5 times x to the 1. No, just x. Minus, here should be an x, right?
Yes.
And maybe it's also a good time to take out the 5. So if we take out a 1/5, Brittany, you following all this algebra? Then this is like 3x minus 4 minus 5x. This is like the professional way to do this.
Yeah.
So it turns out that what we get up here is in the brackets is negative 2x minus 12. Do you agree?
Yes.
And then there's a negative on the outside, and then that whole thing is over 5x to the 2/5. So really what we have is 2x plus 12, or otherwise known as 2x plus 6, all over 5x to the 2/5. Someone back me up there? Good. I guess I'll go with just Griffin backing me up. All right.
I didn't do the problem.
Oh, you didn't even do the.
I know.
That's kind of why I wanted someone else to judge me. All right, that looks familiar. You want to go outside?
Yes.
All right. I guess I'm taking my class outside. So I didn't even finish the problem, but good enough for now. Goodbye, internet.